In this video, we're going to look at 3 different ways for measuring the speed of sound, and all 3 ways are typical ways you will see mentioned in exam questions. So method number 1 is all to do with echoes. Very simple, something that students probably would have come across in year 7, but it obviously takes a little bit of reminder. And then if you're teaching triple, it goes into a little bit more detail because it talks about ultrasound and then talks about the uses of ocean depth or ultrasound scans for medical uses. But in combined science, it's limited really to working out either the speed, the distance, or the time it takes. So a typical question will be something like work out the distance from the person to the wall. The speed of sound is given in air as 330 meters per second. Now, this is actually something that students should remember. They are actually expected to remember it's about 330. If they write 300 or to 340, that's usually accepted. But in this question, I'm going to give it to you. And then the time for the boy to hear the echo is, let's go for 2 seconds. And it says work out D. So really simple. The sound wave travels to the wall, reflects back, and the student hears it. So we're going to be using the basic relationship speed is distance over time. There is, however, one trick to this. Okay, the time is the time it takes for the wave to go to the wall and reflect and come back, but we obviously only want the distance there. We don't want the distance there and back. So at some point, we either need to divide the time by 2, or we need to divide the distance by 2. I'm going to divide the time by 2, so I'm going to say the time to get to the wall is obviously going to be 2 over 1 seconds, which is 1 second. So then I can say that distance is speed times time, 330 meters per second, times by 1 second is going to be equal to 330 meters. Okay, really simple question, really simple idea. Obviously, the numbers aren't always going to be this simple. Sometimes they might expect students to remember this value for the speed of sound. So very closely linked to that is this kind of question here, where it says the time between making a sound and hearing the second echo from a wall is 3 seconds. Calculate the distance to the wall if the speed of sound is 330 meters per second. So we've got the original sound, we've got the first echo, we've got the second echo. The time to hear the second echo is 3 seconds. So if we've got somebody here and we've got a wall, we've got the sound wave traveling this way, it reflects, that's the first echo, it goes back again, it reflects, that's the second echo. So the second echo is at 3 seconds. So the time for the sound to get to the wall, okay, you should be able to see this, is 3 over 4 or 0.75 seconds. And then again, we can use distance is speed times time. And again, the speed is given to us as 330 meters per second times by 0.75 seconds. Plug that into our calculator and we get our answer. So same idea, but they've just tried to confuse it a bit with a graph of a sound wave with a weird axis. But it's exactly the same idea. So this kind of picture here is really crucial for students' understanding. Right, method 2 that we're going to look at is a really nice practical demo that you can set up. Okay, it involves a signal generator and vibration generator, which is basically just a speaker with a stick on it. It involves a string which is put under tension by a weight, which is just some masses, and then we have a known length of string here. When you vibrate the signal generator, when you use the signal generator to vibrate the vibration generator, it will move up and down. And if you are careful and you pick the right frequency, you can create a standing wave. Standing wave is just a wave that is trapped in this fixed space here, and you will see an actual wave. So the first standing wave you get will be what we call the first harmonic, which looks like this. Okay, those are the two ends. And then as we increase the frequency, we will go up through the harmonics, we'll go up through all the different sort of whole half wavelengths of waves. So the next one we will see a full wave. Okay, this is half a wavelength, this is 2 half wavelengths. The next one will be the next harmonic. So we've got 3 half wavelengths or 1.5 waves, and then you can see here we've got 2 whole wavelengths, and that will continue. Then we'll get 2.5, 3, etc. So this is really, students absolutely love seeing this because they can see very, very clearly a wave formed on a piece of string. And then if you go on to A-level, we look at this in a lot more detail. We talk about how this wave is formed by the reflection of the wave and the superposition of the wave, which you can talk about, but is not critical for GCSE students. So here's a picture of the setup. It's not very clear because it's in black and white, but this should also be on the PowerPoint. It's really simple. You get yourself a ruler and you make sure you put the ruler here so you know the fixed length of string. You measure a number of wavelengths. So here I would be measuring 2 wavelengths, and then I divide by 2 to get to 1 wavelength. You know, if I'd measured this, then I'd obviously multiply by 2 to get to 1 whole wavelength. And then simply the speed of sound is the frequency times the wavelength. This obviously comes from the ruler, the measurement, and this frequency, you'll be able to read it off the signal generator. There will be a little box and it tells you what the frequency is. So you just plug in the numbers. The main point with this is obviously we're just talking about averaging over a large number of wavelengths, which is, of course, good for students and their practical skills. And then the final method we're going to look at is the wave tank or the ripple tank. So it's a box like this with a little tank of water on top. And then it has a little motor with, it's basically just a plastic ruler attached. The plastic ruler vibrates up and down and it sends waves along the ripple tank. And if you set it up like this with a light, roughly this angle, the light will travel down without, drowning out the waves, without making it too bright. And you'll be able to see on the screen here the waves. Now this is good because you can project it to the whole class. So from the side, the ripple tank looks like this, and then the light is up here. And importantly, you need to get a plastic tray with a piece of paper on, and you need to put it at about 45 degrees, and you'll probably just need to put a mass here just to jam it. You can see the mass here. Now, when you put the screen here at 45 degrees, obviously the light travels down and projects it to the class. If you don't do this, it's almost impossible to do as a class demo. And it will take a little bit of fiddling about because it does have to fall off, but this will give you a whole class demonstration. You might need to turn the lights off. So what you can do with this is you can take in advance a picture of the ripple tank or the screen, the projection screen, and you will see the water waves, and you'll see that they travel down. And there's 2 methods again that we can use to work out the speed of these waves. We could use speed is distance over time, where we time with a stopwatch the time it takes for the waves to go a fixed distance. It's worth trying to do this, and it's worth trying to do this in front of the class, but you will find that they move quite quickly and it's not always super clear. So actually it's quite hard to do this. The best thing to do with this is actually to send a pulse of waves across the ripple tank. So basically you just turn them on and off, or you turn the vibration generator on and off quickly, and then you can actually see that pulse travel across. Otherwise, if you try and do it when it's constantly sending waves, it's unlikely to work. But what will work is taking a picture in advance, and then you can print it out and give it to students. And then you can tell them to use a ruler, or I've printed a ruler on here, which is also sensible to do. You can tell them to use, again, speed is frequency times wavelength. They're going to measure the wavelength using a ruler. And the frequency, again, comes directly from the signal generator. or you can just make it up, right? It's not the end of the world if you've lied slightly for this, because this is the method they need to use in an exam. So here I've drawn a line to represent the number of wavelengths. We've got 1, 2, 3, 4, 5, 6, 7, 8 wavelengths. 8 wavelengths corresponds to, this is what, 4.7 minus 1, which is 3.7 centimeters. So that's 8 wavelengths. So 1 wavelength is obviously 3.7 divided by 8. And then you plug that into this formula with the frequency from the signal generator and work out the speed. This is really good for two reasons. One is, again, it shows students the importance of averaging over a number of wavelengths. Also, it's a really nice example of uncertainty here, right? Because this, as you can see, is the thickness of the wavefront, and actually where exactly do we measure the wavelengths from, right? You can measure it from the middle, but again, this one's thinner, this one's fainter, this one's really thick. So it's a really nice discussion of uncertainty, and you could even give your answer in terms of wavelength. You know, you could say it's 4.7 plus or minus, 2 millimeters, for example. And then you could explain to students what we mean by this kind of representation of uncertainty. And therefore, when we get a final answer, it's going to be a velocity plus or minus some number.